So today what we're going to do is we're going to learn how to solve a logistic differential equation. But before I even get into that, we need to talk about what a logistic function is. And what you see right here is a logistics function. And what it does is there's a limiting factor to how much it grows. So it grows kind of exponentially at first, but then it plateaus because of resources. So the pandemic right now, this is a perfect example of a logistics curve because it is going to eventually wane down right here, and it's going to start slowing the spread, right, until it reaches its carrying capacity. So populations do this too. So the virus, the pandemic, is just an example of a population of virus, all right? So right here, for this bear population, time in years, right, on the horizontal axis, this 100 is a horizontal asymptote, and that is the carrying capacity. That's the maximum value that the bear population could ever reach, okay? So we call this the carrying capacity. And a logistics function always looks like this. It's for like population, okay, for a given period of time. In this particular equation it's going to be 100 over 1 plus 9 e to the negative 0.8 times t. And a logistic function always takes on this form. And we can look at this and realize, okay, this right here is the same as my carrying capacity, all right? So this number, this numerator on a logistics function will tell us the carrying capacity. This is determined by growth factors and other things, and this 9 is by the initial conditions. We're actually going to come up with this later on as the very last part of this problem, okay? So when you go to take the derivative of this with respect to t, you wind up with a logistics differential equation. And a logistics differential equation, it's really kind of a simple equation, all right? And I'm not going to go through where we get this, but what we wind up for differential or a logistics differential equation is we wind up with something like this: 0.008 times the population times 100 minus p. And so when we're given this logistics differential equation, this is what the graph of the derivative is. And if you multiply this out, this would give you the population. Okay, so the growth rate is determined by the population, not necessarily the time. Okay, so if you look at this, this is just a quadratic. All right, and if you look, when was the bear population growing the fastest? Well, it's always going to happen on a logistics curve. It's always going to happen halfway between 0 and the carrying capacity. So that would be at 50. So that is right here. And that's when the growth happens, the maximum growth happens. That also shows up on the differential equation as a maximum right here. So it's in between the 0 and the carrying capacity, and that's when the maximum growth will always happen. Notice even in the logistics differential equation, we can still see the carrying capacity. It'll be right here. It'll be that number that's right there. Okay, so this is still the carrying capacity. That's the maximum population could be based on resources that the environment has. All right, so let's go and do a problem now. So these problems are very similar to what you're going to see on homework, okay? So the growth rate of a population P of bears in a newly established wildlife preserve is modeled by the differential equation dP over dt equals 0.008 P times 100 minus P, where T is measured in years. What is the carrying capacity for the bears in the wildlife preserve? Well, we can just look at this and go, okay, right there, that number right here is always going to be the carrying capacity, okay? So the carrying capacity is 100 bears. And so if it's not in this form where it's a number minus p, you need to rewrite it so it takes on this form, and then you can see you can see what the carrying capacity is once you write it in this form. All right, that's what I was trying to say. Okay, so what is the bear population when the population is growing the fastest? Okay, so we know it's going to be growing the fastest when it's halfway to the carrying capacity. So that's when the population is growing the fastest, when the bear population is 50 bears. Okay, so the population is growing fastest at 50 bears. It will always grow, a logistics function will always grow the fastest halfway to the carrying capacity. So carrying capacity is 100 bears, so this is 50 bears. Okay, and then how is it changing? What is the rate of change of the population when it is growing the fastest? Well, dp over dt is all determined by the population, right? How much it's changing is determined by what the population size is. So for this, we know that dp, let me slide this up a little bit. We know that dp over dt is equal to 0.008p times 100 minus p. And so we want to find this when it's growing the fastest. Well, when it's growing the fastest is when p is equal to 50 bears, right? So we want to find dp over dt at p equals 50. So that would be 0.008 times 50 times 100 minus 50. And so that would give us 0.008 times 50 times 50. And if we put that into our calculator, we wind up with 20. And what are the units for this? Well, the P is the population of bears, right? And T is time, and we're measuring time in years. So this would be 20 bears per year. And that would be the units for this. Okay, let's do one more problem. So we want to solve the differential equation with the initial condition P of 0 is equal to 10. Well, we know that dP over dt is equal to 0.008 p times 100 minus p. And so what we want to do is we want to do separation of variables, right? We want to get our p's and dp's on one side and our t's and dt's on the other side, right? But we don't really have any t's, we just have p's, right? So what we need to concentrate when we see this is we need to get the p and the 100 minus p over to the other side. So we're gonna have to divide by that and multiply both sides by dt. So what winds up happening is this becomes 1 over p times 100 minus p dp is equal to 0.008 times dt. And what we're going to want to do next is integrate both sides. So we're going to integrate this side. So 1 over p times 100 minus p dp is equal to the integral of 0.008 dt. All right, so now here's the problem. What we have to do to integrate this left-hand side, this one's going to be easy because this would be just 0.008 t plus some constant c, right? That's what this is going to be because this is just a constant. And so this one, we have to figure out how to do this one. Well, that's why I taught you partial fraction decomposition. We're going to need that partial fraction decomposition to integrate a logistic differential equation. So what we have is we have 1 over p times 100 minus p is equal to, all right, so it's going to be a over p plus b, which we don't know what b is, right, times 100 minus p. All right. So the next thing we're going to do is we want to clear out our fractions. So we're going to multiply by p and 100 minus p. So that's going to give us 1 is equal to, when I multiply this by this denominator, right, the p's are going to cancel. So I'd be left with a times 100 minus p plus, and then when I multiply this fraction by the p times 100 minus p, the 100 minus p will cancel and be left with b times p. So to get rid of the a, we're going to let p equal 100, and that would be 1 is equal to, well, when p is 100, this is going to be 0, so this is going to go away. So 1 is equal to b times 100, or 100b, which means 1 over 100 is the same as b. Okay, to get rid of the b and figure out what a is, we're going to let p equal 0. So when p equals 0, we'd have 1 is equal to a times 100, or that's 100a, plus b times 0, which would be 0. So this would be 100, 1 over 100 is equal to a. Okay, so that means this a right here is 1 over 100, and this b is 1 over 100. So that would mean that 1 over p times 100 minus p is equivalent to 1 over 100 over p, because that's my a over p, plus my b, which is 1 over 100 over, this fraction bar should be a little bit longer, okay, and 100 minus p. Okay, so that means this integral right here can be replaced with this integral. All right, so now what we have is the integral of 1 over 100 over p plus 1 over 100 over 100 minus p dp is equal to the integral of, and this would be this right hand side, the integral of 0.008 dt. Now, what I would do is I would multiply both sides of this equation by 100, okay? Because that's going to make this become 1 and this become 1, and that's going to move the decimal over a little bit. So what I'm going to do is I'm going to multiply both sides by 100, because that will clear out my fractions and move my decimal over. I'll have a little bit of a smaller number here. Okay, so this, if I multiply this outside by 100, that means I would have to distribute it, which makes this become 1 and this become 1. So this would be the integral of 1 over p plus 1 over 100 minus p dp is equal to, and if I multiply this by 100, okay, this is 8 thousandths. So then if we multiply that by 100, we get the integral of 0.8 dt. And this is a little bit smaller number to work with, or a bigger number, I should say. All right, so now what we need to do is we need to integrate this. So this would be the integral of, and I'm going to slide my paper up a little bit. The integral of 1 over p dp plus the integral of 1 over 100 minus p dp is equal to the integral of 0.8 dt. This one's ready to integrate. This one's not, okay? I would do an integration by substitution here. So I'm going to let u equal 100 minus p. And then du would simply be negative dp. Okay, so I'm gonna put a negative on the outside here and on the inside. Okay, so I'm gonna have a negative dp and a negative on the outside. So I'm gonna, in essence, multiply by -1 times -1. So this integral becomes 1 over p dp minus the integral of 1 over u and then du is equal to the integral of 0.8 dt. All right. So then what happens here is this is the natural log of the absolute value of p minus the natural log of the absolute value of u is equal to, and this would be 0.8t. And then we got to remember plus some constant c. And the way we're going to figure out this constant is by the initial condition that was given to us. So swapping this back out, okay, I'm going to change my u back to 100 minus p because we need to do that. So this becomes the natural log of the absolute value of p minus the natural log of the absolute value of 100 minus p is equal to 0.8 t plus some constant c. All right, and then one more thing that I'm going to do that will help clean this up a little bit is I'm going to multiply both sides by -1. Now, this one, because it's a constant, right? We don't know what this is, so we can just keep it as plus c. So what happens is this is going to become positive, and this one's going to become negative. And so this is the natural log of the absolute value of 100 minus p minus, because that's going to change to a negative, the natural log of the absolute value of p is equal to negative 0.8 t plus some constant that we don't know yet, c. Okay, so you don't have to write this as minus c. Okay. Now, the population, the bear population, is between 0 and 100, right? It's between 0 and 100. So really, in this case, we really don't need the absolute values. So we can rewrite this because the biggest the population, and it can actually never reach this, is 100, right? That's the carrying capacity. So this would be the natural log of 100 without the absolute value minus p minus the natural log of p is equal to negative 0.8 times t plus some constant that we don't know yet, c. All right, so we have this, and now the next thing we're going to do is we're going to go and we're going to figure out, okay, or we're actually, there's another way we can write this one using logarithm properties. Remember, if we have the natural log of a minus the natural log of b, that's equivalent to the natural log of a over b. So we're going to use this to rewrite this in this form right here. All right, so I'm going to go to my next page. So we now know from that last page that the natural log of 100 minus p over p is equivalent to negative 0.8 times t plus some constant c. Okay, and we also know from the very beginning that p of 0 is equal to 10. Now this 0 is my t, and this 10 is my p population. So I can put 0 in for t and 10 in for p, and I'll have it, okay? So this becomes the natural log. I'm figuring out what c is. I'm plugging in my initial conditions. So this is 100, natural log of 100 minus 10 over 10 is equal to negative 0.8 times 0 plus c. So this would be the natural log of 90 over 10, because 100 minus 10 is 90, is equal to C. Now this can be reduced and we'd have 9 over 1, which is 9. So the natural log of 9 is my constant C. All right, so now I can go back and write this. This is the natural log of 100 minus P over P is equal to negative 0.8 times T plus the natural log of 9. And the next thing I want to do is I want to exponentiate both sides. So this is going to be my exponent to get rid of this natural log. And so these are going to be my powers. So this becomes e to the ln of 100 minus p over p is equal to e to the negative 0.8 t plus the natural log of 9. So my e to my ln are going to undo each other, all right? And so we're left with 100 minus p over p is equal to, and because I'm adding these and they're exponents, that means I could rewrite this as a product. This would be e to the negative 0.8 t times e to the ln of 9. But e to the ln, these are going to undo each other, so this is just going to become 9. So we have now 100 minus p over p is equal to e to the negative 0.8 times t times 9. All right, so now it's a matter of, okay, how do I solve this for p, right? So what I'm going to do, and we can write this as 9e to the negative 0.8 t, and that's what I'm going to do next. And I'm going to multiply both sides by this p, okay? So if I multiply both sides by p, I would have 100 minus p is equal to 9e to the negative 0.8 t times p. And so now it's a matter of getting everything with p on one side, all right? So we're going to get this, let me slide it up. We're going to move this because this is 9e to the negative 0.8 t times p. I'm going to add p to both sides. And so I wind up with 100 is equal to 9 e to the negative 0.8 times t times p plus p. And so what I can do next is I can factor out a p out of both of these. So 100 is equal to p times 9e to the negative 0.8 t plus 1. And then I can divide by this and I'll have p by itself. Okay, so this would be 100. And I'm going to write the 1 first because that's the traditional way of writing it. Okay, so if we're adding this, the order doesn't matter because we're adding, right? So this is 100 over 1 plus 9 e to the negative 0.8 times t is equal to p. And that's the form of logistics function, which that was it. We started with a logistics differential equation. So that's going to give us a logistics function. Okay. All right. So, and we got that through partial fraction decomposition, integration by substitution, separation of variables, plugging in our initial conditions. All of those things we've talked about is how we come up with this. A lot of different math techniques were used in solving this. Okay, that's why we're only going to do one. All right. And if you take a look at our starting problem, this was our initial problem. Okay, if you go back to the first page, this is what we had to begin with, right? Right. And if we take the derivative of this, this is what we can wind up with. It's all based on the population P. All right. Okay, so you may wonder why, let me grab this, why right here, and I really didn't do, I don't think I did a good enough job explaining it. Why right here did I multiply both sides by this negative? It's because I knew this was going to wind up being an exponent, and for it to be a logistics equation or logistics function, all right, what I need is for that to be a negative, okay? Because on a logistics function, this exponent right here is always going to be negative. All right, so that was kind of me knowing where I was going with this, of why I wanted to right here, going from I lost it, going from here to here, why I multiplied both sides by -1, and because that switched the order and caused this 0.8t, which is positive, to become negative. All right. All right. So that's it for that. That's logistics differential equations. You really have to get the carrying capacity and know and recognize, okay, I can get the carrying capacity from the logistics function, but I can also see it from the logistics differential equation. It's always going to be this number right here that you're taking P away from. All right. That's it, guys.